Hello everyone. The topic of my presentation today is microstructure and evolution characteristics of hafnium carbide ceramics, which are derived from a commercial precursor. First, I will give a brief background and motivation behind this study. As we all know here, there is a huge demand for more efficient and powerful aircraft and spacecraft engines, which require more severe operating conditions, such as higher temperatures, faster speeds, higher stresses, and hostile environments. Now, high temperature metals or metal-based superalloys, such as nickel-based superalloys here, have played an important role in the development of aerospace propulsion, along with cooling systems, and also in vehicle structural thermal protection systems. However, the increasing temperature of the operating conditions in future aerospace transportation, such as high-efficient jet engines or a hypersonic aircraft, which is shown here, where the engine is an integral part of the body itself, limits the choice to very few high-temperature ceramics. Now, existing high-temperature alloy materials have poor oxidation resistance, and their application temperatures are generally lower than 1200 degrees Celsius. Where the ultra-high temperature ceramics generally have melting points higher than 3000 degrees Celsius and also have excellent oxidation ablation resistance. As a result, these ultra-high temperature ceramic materials can maintain structural integrity in an oxidizing environment above 1800 degrees C for a longer period of time, and this makes them very promising for applications in extreme conditions. On the other hand, ceramic matrix composites such as carbon-6, advanced carbon-carbon, or 6 materials, which are grouped together here, may retain high strength at elevated temperatures, which are key for air-breathing vehicles. However, long-term application temperature for carbon-6 material could not exceed over 1650 degrees centigrade due to the active oxidation of the 6 matrix. Also, carbon-carbon matrix starts oxidation above 500 degrees C without a protective layer. Now, monolithic hafnium carbide may survive over 2000 degrees C. However, they are susceptible to catastrophic failure during their services. Now, the goal is to achieve high specific strength at elevated temperature, which is shown in this region here. And one solution could be to include ultra-high temperature ceramics or ceramics matrix into the fiber preform. The earliest research on this ultra-high temperature ceramics, specifically hafnium bromide and zirconium bromide, can be traced back to 1950s, where they were used as nuclear reactor materials because of their excellent high temperature corrosion resistance. Then in 1960s to 1980s, Air Force Research Lab explored the potential of ultra-high temperature ceramic materials for anti-oxidation and ablation resistance. However, by the end of 1990s, and also in the beginning of early 2000s, the intrinsic brittleness of these materials were discovered during a flight demonstration. A better solution then was proposed to introduce this ultra-high temperature ceramics to continuous fibers. And since then, the research on this ultra-high temperature ceramics has taken a rapid increase in the number of relevant publications over the years. In this work, a commercially available single-source and liquid-phase hafnium carbide precursor was utilized to manufacture hafnium carbide powders. Various cross-linking temperatures were studied to determine the low-temperature curing conditions for the precursors, followed by pyrolysis at 1600 degrees centigrade for 1 hour in an R1 environment. The curing conditions that are shown here were determined by our industry partners. The precursor was thermally cross-linked at these 5 different conditions, and the figure shows these 5 different samples. They were cured at 5 different stages. Several characterization techniques were used to evaluate the polymer to ceramic evolution and microstructures in hafnium carbide ceramics, and some of those characterizations are presented here. The polymer precursor was investigated using liquid state NMR to determine the molecular structure of the precursor. In addition, FTIR was utilized to determine the polymer structure of the precursor and also the transformation of the precursor from liquid to cross-linked samples at different temperatures. Now, according to NMR and FTIR, the liquid precursor contained hydrated hafnium oxychloride. Here in the FPIR plot, as the cross-linking temperatures increased from 105 to 400 degrees C, the intensity of the vibration bonds for the water molecules decreased significantly due to the release of water. For these three samples, sample S3 to S5, the magnified image of this region is shown over here. Here we see a shift at the peaks, which are presented here around 1600 per centimeter. This supposedly happened due to the coordination of cations in the cross-linked structures of hydrated hafnium oxychloride. Absorption peaks corresponding to monoclinic hafnia were also vaguely visible at lower wave numbers for this sample. Now, TGA of one of these cross-linked samples was performed in presence of air, and three mass loss regions were observed at temperatures below 1600 degrees C. This mass loss was attributed to the release of evolved gases such as water vapor and volatile gases, for example, carbon monoxide, carbon dioxide, methane, and chlorine. X-ray photoelectron spectroscopy, or XPS, was performed to confirm the elemental composition and determine the chemical bonding of the elements in the synthesized hafnium carbide ceramics. The presence of hafnium and carbon along with oxygen in the pyrolyzed samples suggested the formation of hafnium carbide ceramics in the pyrolyzed samples. As presented in this table here, chlorine was observed in the cross-linked hafnium carbide precursors, which was completely absent in the pyrolyzed ceramic samples. XPS spectra shows the increase in carbon for the and also decrease in oxygen for this S3 to S5 samples compared to S1 and S2. This indicates that curing temperatures plays a significant role in the composition of the final ceramics, as the presence of moisture and oxygen largely depend on these temperatures. This figure shows here the high-resolution hafnium, carbon, and oxygen spectra and the chemical bonding states of these elements. The hafnium profile showed the presence of hafnium carbide peaks for hafnium 4F doublet. Hafnium oxide peaks were also observed for all the samples. The carbon spectra also showed the presence of hafnium carbide bonds along with the presence of free carbon in the ceramic structure. For oxygen spectra, the peak was assigned to the oxygen atoms in hafnium. This figure presents the XRD characteristics of the hafnium carbide ceramics pyrolyzed at 1600 degrees centigrade. The presence of crystalline hafnium carbide and monoclinic hafnia were observed for all the samples. As this figure shows, the intensity of hafnium carbide increases and the intensity of hafnia decreases. This behavior was again related to the various curing temperatures of the samples. Here, sample S1 and S2 were cured at 105 degrees centigrade for 1 hour and 4 hours respectively, and the moisture would still be present in this sample after curing. The samples were transferred from the glove box to the furnace for pyrolysis, and the intense monoclinic hafnia phase in these two samples could be attributed to the hydrolysis reaction during transfer in air. With the increase in cross-linking temperatures from 250 to 400 degrees C for this sample S3 to S5, the presence of the moisture in the cross-linked samples was greatly reduced. As a result, a clear increase in hafnium carbide peaks were observed for all these samples. In addition, traces of carbon materials were also observed in all the samples. Here, the crystal structures of the hafnium carbide and also the monoclinic hafnia are shown, which are presumably present in these samples. To determine the formation characteristics of hafnium carbide ceramics at different temperatures, the cross-linked samples S2 and S5 were pyrolyzed at different conditions. Here, the XRD of these samples pyrolyzed at 1600 and 1000 degrees centigrade are presented. As expected, at a lower temperature of 1000 degrees C, we see mostly hafnium oxides were present in the ceramics, whereas with the increasing temperature to 1600 degrees C, the hafnium carbide becomes prevalent in both cases. especially for samples S5, which were cured at higher temperatures compared to sample S2. The hafnium carbide peaks were more prominent than hafnium oxide peaks. This results corresponds well to the data from the literature, where you can see with the increasing temperature of the pyrolysis, the intensity of hafnium carbide crystals also increased. Now, to investigate the morphology and particle dimensions of the hafnium carbide ceramics, which were pyrolyzed at different temperatures, SEM analysis was performed. At a lower temperatures of 1000 degrees centigrade, both these samples showed agglomerated lumps in the powders. These agglomerated lumps supposedly consisted of hafnia and amorphous carbon, which reacted intensively to form hafnium carbide at higher temperatures. As a result, at 1200 degrees centigrade, the crystalline particles started to appear, and at 1400 and 1600 degrees centigrade, well-defined crystalline particles with narrow size distributions were observed. The particle size of these samples was determined to be in the range of 600 to 700 nanometers. Elemental analysis, which was determined by X-rays, showed a strong presence of hafnia along with carbon and oxygen in these samples. These SEM micrographs were then compared with the data from literature. Similar results were observed for the samples pyrolyzed at 1000 degrees C, where we see agglomerated lumps of hafnia and carbon in these samples. With the increase in temperature to 1200 degrees C, hafnium carbide crystals starts to appear. However, at 1400 and 1600 degrees centigrade, we can see well-defined and separated hafnium carbide particles, which is not the case in our samples. And also the particle size here, in this case, was in the range of 100 to 200 nanometers. Now, the precursor that was used in this study was hafnium chloride and citric acid dissolved in distilled water. And the samples were initially pyrolyzed at 800 degrees C, which were then further annealed for 1 hour at higher temperatures, which suggests that any additional annealing may produce separated or equidistant particles in our samples as well. The hafnium carbide powders were then oxidized in the presence of air for an hour at different temperatures, and they showed oxidation even at 600 degrees centigrade. This result is expected as hafnium carbide starts forming hafnia in the presence of oxygen at temperatures even at 500 degrees centigrade. However, when combined with silicon carbide or silicon carbonate, hafnium carbide forms a phase which can deter oxidation at higher temperatures. So the next logical steps for us is to use these precursors to fabricate a multi-phase hafnium carbide silicon carbide ceramic. We have fabricated a multi-layered multi-phase hafnium carbide silicon carbonate ceramic matrix composites using these precursors, and this ceramic matrix composite will be tested further in future to determine their suitability for high temperature applications. To summarize and conclude my presentation today, we have used a commercial hafnium carbide precursor to determine its thermal behavior at different curing and pyrolysis temperatures. The NMR and FTIR characterizations were utilized to determine the precursor's composition, which is hydrated hafnium oxychloride. SEM micrograph suggested that the hafnium carbide crystals starts to appear above 1000 degrees centigrade. The XRD analysis confirmed the presence of hafnium carbide along with monoclinic hafnia and free carbon in the pyrolyzed structures. Future work involves the fabrication and high temperature testing of this multi-layered, multi-phase hafnium carbide silicon carbonate ceramic matrix composite. Thank you for your attention. Please let me know if you have any questions.